All right, folks, welcome back for the second plenary of the day. First up, we have Hsin-Yu Chen from the University of Texas. Take it away.
All right. Hi, everyone. I'm Hsin-Yu. I'm assistant professor at UT Austin. And today, this is gonna be a gravitational cosmology talk, but we already heard a very nice review on Monday by Chiara about the cosmology aspect. So this talk is gonna go into more details about the standard siren approach, and we'll cover both the ground-based and the ground-based and space-based mission in the next decade. Okay, so. All right. If we can get it work. Down. Down.
You have to point it though.
Oh, I need to point to.
It might be off because I was charging.
No, it just worked. I just checked it.
My fault.
Oh, okay. Power is not on, sorry. Yeah. Okay. All right. So we all know that we had a lot of powerful cosmologic probe from, say, CMBs to galaxy survey to supernova observation over the last several decades. And all these powerful experiments help us to shape our knowledge, our understanding about the universe. The standard model for cosmology. The observed universe appear to have very good agreement with this standard model, also known as the lambda CDM model. However, is this model good enough? To answer these questions, we have to ask, well, do we have any experimental result that we don't know how to explain? And we do. The most famous one is the Hubble tensions. We have the type 1a supernova measurement of the Hubble constant, the local universe expansion rate, placed out by the Schultz team. They are inconsistent with the one inferred from the CMB observation. Currently, the tension is as large as 5 sigma. They're not the only H0 measurement. We have plenty of them that's summarized in this plot. I know you cannot reading the details, but the idea here is they lie all over the places. We also have a milder tension. This is in the SA, the quantity that describes the clustering of the matters in the universe. Again, the measurement from the value inferred from the CMB observation is inconsistent with the weak lensing observation at the 2 to 3 sigma level of tension. The more recent one, the one of the dark energy equation state measurement by the DAISY experiments from the BAO observations, appears that maybe the dark energy equation of states is not a constant. Maybe they evolve over redshift. So with all these mysteries, these tensions, could they come from some unexplained systematic among these experiments? Or do we need a new theories to explain the cosmology? Do we need to modify it? That has been the big debates over last decade or more. And this is where the gravitational wave cosmology, our standard siren methods can play a role. Since if we can capture the gravitational signal from these compact binary mergers, either from the space or the ground-based missions, and even better, if we can capture their electromagnetic counterpart, then we can conduct this standard siren measurement that will give us an independent measurement of the cosmological parameters. And that might help us to say something about these mysteries, these tensions. So the plan for this talk is the following. We're gonna quickly go through the standard siren methods. There are different type of approaches. I'm gonna give out the projections, make some comparisons, and give you some final thought about this. Okay, so let's start with this Hubble's law. Hubble's law tells us that if we are able to measure the distance to an astrophysical object, and also their redshift, how fast away they fly away from us due to the cosmic expansions, then we can place constraint on the Hubble parameters, how fast, what is the cosmic expansion rate. And in the local universe, that becomes the Hubble constant H0. If we start with this measurement from the EMM side, then it's typically more easier for us to determine the redshift. It is a distance that's difficult. But if you start the observation from the gravitational wave side, the story reverse. It is straightforward for us to determine the distance. It is the redshift that's actually difficult. And how we determine the distance? Well, if we start with our compact binary mergers, they emit a gravitational wave signal received by our detectors. We know that the amplitude of this signal goes inversely as the distance, which means if these sources, they were further away, then you'll have a smaller amplitude. So from the amplitude of this signal, we can determine the distance to the source. The redshift is the difficult part for us. So if we are able to capture the gravitational signal, we are actually not doing a very good job on localizing those sources on the sky. For LISA sources, we are typically talking about maybe order of 0.1 to 1 square degrees localization on the sky. And for people who are not familiar with this unit, for comparisons, the full moon has the size of around 0.2 square degrees on the sky. So you can imagine having something like this, 0.1 to 1 square degrees is still a large area on the sky, and there's also an uncertainty over the distance. So within this localization volume, there are too many possibilities. We don't know where to point your telescope to measure the redshift, and that is the difficulty. This difficulty can be almost overcome if we can capture their electromagnetic counterpart to these gravitational signals. And that is because these traditional telescopes, they do a much better job at pinpointing the source on the sky. Then with this very precise localizations, we can associate the gravitational source to their host galaxies. Then by measuring the redshift of this host galaxy, we can determine the redshift of this gravitational signal and then place constraint on the cosmological parameters. This approach is known as the bright siren because we are using the EMM signal. And it was realized with the very first time from this most famous event, GW170817, the binary neutron star merger detections. After that detection, LIGO Virgo put out this sky map, that red island you see there. And then the astronomer tried to look for a potential electromagnetic counterpart for this event that led to this kilonova discovery. And that big blob next to it, that was the host galaxy for this event. So from the redshift of this host, we combined it with the distance measured from gravitational wave side, and then make the very first measurement of the Hubble constant with the standard siren method. What you see here is the posterior of this H0 measurement. However, when we place back the tensions I mentioned at the beginning, we did not resolve any tension there. But the hope 10 years ago was that we are gonna get more and more events like this, and then our H0 posterior is gonna shrink over time. And here's the reality. The reality is that over last decade, we only capture about a handful of handful of detections that could possibly host EM counterpart, including some binary neutron star and some neutron star black holes mergers. But out of those around handful of events, we still stay with this only one EM counterpart with the GW170817. That's the only bright siren we have so far. On the other hand, we have detected more than 300-400 of binary black holes mergers. They are dim. They don't have electromagnetic counterparts, but there are so many of them. So could we try to turn them into something useful for cosmology? Yes, that is possible. Because they don't come with electromagnetic counterparts, so when we fall back to this picture of pool localization area, localization volume on the sky. And within this localization volume, there can be so many possible potential hosts for these gravitational signals. In principle, if we capture all of these galaxies, we measure their redshift, we can statistically combine all of them. And then, since one of them should be the real host, after you repeat this for multiple events, eventually you will place some constraint on cosmology. This is known as the dark siren approach from the name, because we are not using electromagnetic counterpart. However, there are also plenty of challenges with this approach. As you can imagine, we are talking about we need all the galaxies. So incompleteness of the galaxies is one big challenge for this approach. Another problem is these different galaxies, they have different possibility of hosting the gravitational event. So if you are placing incorrect weighting for each galaxy, you're gonna introduce systematics. And more fundamentally, for most of the gravitational events we detected so far, they are localized, again, poorly. So you got too many galaxies within this volume, and the measurement becomes uninformative, okay? But we're still trying. So with all this challenge, people are still trying, and there is yet another possible approach, which is trying to use the redshift, the cosmological redshift of the gravitational wave signals. We'll know that for the EMM wave, when they propagate through the universe, they got redshifted. Something happened to gravitational wave sources after they propagate through our universe. They also they got redshifted. Frequency become lower, and this kind of redshift will make the system originally, let's say, having some mass m, looks heavier. So in principle, if we know how the mass distribution of these gravitational wave sources should look like their real mass distribution, we also call it the source frame mass distribution, then depending on what kind of cosmic expansion history it goes through, you will end up with different kind of observed mass distribution. You also call it the detector frame mass distribution. So by comparing the two, by comparing what you detected to what it is supposed to be, then you should be able to place constraint on cosmology. This approach specifically relies on the peak and trough in this mass distribution, just like those peak and trough in the electromagnetic wave spectrum, and that is why this approach got the name of spectral siren. Okay? And nowadays, when we are really applying this approach to avoid extra systematic introduced by your assumption of the intrinsic, the real mass distribution, what we really do is that we jointly infer both the cosmological parameters and also the population parameter that describe the shape of this mass distribution altogether to avoid systematics. This approach can be powerful because it not only allows access to all these hundreds of binary black holes merger events. You can imagine we can also, in the future, we can use them for source that's very high redshift, because that is where we don't have galaxy catalog. We may not be able to observe the electromagnetic counterpart even if they are there. So spectral siren is kind of powerful in that sense. Okay, so here is the latest standard siren measurement put out by LIGO Virgo Cagra with our GWTC5, the newest galaxy, newest gravitational catalog. It combines over 200 binary black holes mergers with several extra neutron star mergers. And we end up with that black H0 posterior. We are talking about around 10% precision on H0 measurement here. And the contribution, the constraints mainly come from the GF17, OA17, the bright siren, and also the spectral siren. What about the dark siren? Dark siren didn't really do much for this measurement, and the reason is summarized in this plot. So what you see here is the coverage of the galaxy catalog we use for the dark siren inference. We use two different catalogs. The one on the top, called the Glade Plus, that one have a very good coverage on the sky, very wide. However, it's too shallow. The one at the bottom, that is a DES catalog. It goes much deeper, but too narrow. And that is why currently dark siren is not on its full power yet. Okay? All right, so now those are the ground-based standard siren measurements so far. What will be different in the LISA era? Apparently, first of all, the source we are using for the standard siren will be different. For ground-based detectors, we are talking about those stellar mass compact binary merger, binary black holes, binary neutron star black holes mergers. For space-based, for LISA sources, for LISA, we can see some stellar mass black hole binary, but what we really are gonna rely on will be those massive black holes binary and also the Emery. Those are so it's not only about the different type of sources, also it's because they are different type of sources, we detect them at different redshift range, and redshift is what matters for cosmological measurement. So that is yet another difference. So let's say we start with a stellar mass black hole binary. We don't see them very far with LISA, it's really local. For Emery, we can reach them further away, maybe beyond the star formation peak. And then for massive black holes merger, we can see them very far away, out to very high horizon. And because of this difference, we are gonna apply accordingly different type of standard siren approach to do cosmological measurement. Starting with the stellar mass black hole binaries, they are relatively local, so they are best for H0 measurement, the local universe expansion rate. They don't come with electromagnetic counterparts, so dark siren, spectral siren makes more sense. Although there are still tentative claim for possible EM counterpart associating with it to be confirmed. So the projection is with maybe 10 to 100 dark siren, we will reach the level of maybe a few % of Hubble constant measurement. The realistic projection for the number of these kind of sources is something around handful to 20, okay? So we probably don't get too much constraint from there. But let's move on to Emery. So Emery does much better, because Emery, we can see them further away. So we can not only measure the H0, we actually can constrain also, for example, the dark energy equation state. They are higher redshift sources. They also we don't expect electromagnetic counterparts, so we are doing, say, dark siren. With dark siren, 10 to 100 of them, we'll be talking about maybe around 10% level of constraint on the dark energy equation state. Finally, to our most excited source, massive black holes, massive black holes binaries. They're excited because, first of all, we can see them very far away across different redshift. They come with electromagnetic counterparts, so we can have bright siren. And the projection is we'll be talking about maybe % level of constraint on both the H0 and omega matters. Okay? However, the best constraint will come from joint force. So you can try different kind of combination. For example, you can try to combine the different type of standard siren sources across LISA detections. And here is a great examples. For example, Emery cover the redshift range that's relatively lower comparing to the massive black hole binary. So we can let Emery to take care of those measurements at lower redshift, and then you will have an anchor at higher redshift from the massive black hole's binary. And after you do that, this is the power of joint force. So what you see here is a posterior, two-dimensional posterior in the H naught and the omega matter plane. The red and blue are individual constraints from Emery dark siren and the massive black hole binary bright siren. The black is the one after you combine them. Same improvement happen when you try to constrain the dark energy equation of state. So with the joint force, we are talking about under 10% level of precisions for the dark energy equation of state with 4 years of observations. Another way of combining different measurement is you try to combine the space and the ground-based observations. So back to this redshift coverage plot, we said that the LISA can detect some stellar mass binary black holes in spiral, but we only detect a few of them. So it's not a major strength for LISA. However, those are the major source for the ground-based detectors. We detect a lot of them, and sometimes we even see neutron-star mergers, and they can be bright sirens. So why don't we let them to take care of the measurement, the constraint in the local universe? And then, again, we use those LISA sources, the massive black holes binaries, to give us constraint at high redshift. After you do that, again, you can see that red island is after you combine all these different experiments. And by the way, this is a work led by my student, Alberto. I'll wait for a second for Deirdre to take a picture for that. Thank you. Yeah, and send it to Alberto. Yes, okay, yeah. So let's take a little bit closer look to this, because I want to show you the fractional uncertainty on the Hubble parameters across the redshift so that you can see the full strength of this. So let's start with only the ground-based constraint. So that is the blue curve you see there. That is only using the ground-based bright siren and the spectral siren for, let's say, 5 years of observation. We'll be talking about maybe 1 to 2% level of precision on the Hubble constant. But on the Hubble parameters, we'll be talking about maybe around 15% precision at redshift of 1. And that is already using the spectral siren, those thousands of binary black holes merger detected by LIGO-Virgo-Kagra. But that constraint can be improved by a lot once we have the LISA bright siren. And what I'm showing you here is only using less than 5 LISA bright siren. Already it can help you to improve the H of Z constraint by a lot. And actually, LISA bright siren will do so good that after you have that, it makes no point of combining the LVK spectral siren. We're talking about thousands of binary black holes merger information there. Still, they're not gonna win. So LISA bright siren will be very critical for constraining H of Z at a higher redshift. So in summary, we are talking about a percent level of constraint on the Hubble parameters across different redshifts in the next decade. Now, will all this measurement, this sounds great, but will all this measurement to be, well, interesting, relevant 10 years from now? I would say possibly, because I would say that the emphasis for the gravitational wave cosmology here is not to try to compete the precision of the measurement to the EMMs, because if we really compare the precision, we are kind of comparable, or sometimes we are even worse. So that is not the emphasis here. The real role for the gravitational cosmology here is trying to provide an independent measurement that possibly there are some very difficult, unresolved, systematic among those other EMM experiments that we may try to say something about it. Okay? And following that point, then what do we need to prepare for our gravitational wave cosmology science, the standard science? Well, I would say we need to be very careful about the systematic. We want to be, because that is our major role. We don't want to introduce extra systematic in our experiments. Yeah. And also, as I emphasized already, LISA bright sirens will be so important, so development along the line of EMM observing program and also the EMM counterpart theories, those will be critical. We don't want to miss them. All right, I'll stop here. Thank you.
All right, questions. See one right up here.
On your slide that showed combining the Emery and the massive black hole measurements, they had different correlations. Even though it's fundamentally the same measurement, do you know why the correlation direction is a little bit different for those?
What do you mean by fundamentally the same
Just
measure?
the dark siren with a gravitational wave error volume on the sky. So what's different about Emery's versus massive black holes?
They cover different redshift range. So, and also one of them, well, that doesn't make a difference, but they cover different redshift range. So they will give you different shape on that plane of, let's say, the H naught and the omega matter plane. Just depend on where they are, how high the redshift is.
All right, more questions. Right there.
For your LVK predictions of the accuracy of this thing, do you include Einstein telescope and next generation ground-based detectors? How do they impact the results?
If you, I have a backup slide here. So this is what happened. So my title only covered next decade, singular. But now, if we are talking about ET and CE, then this is a projection. So in 20 years from now, then we have ET and CE. Now that the spectral siren could start to play some important role, this is a projection. Let's see. This is we are to be talking about sub% level of constraint. And notice that this does not include bright siren. So just the dark siren, just the black holes, mergers, basically, is going to give us sub% level of precision because we're going to get so many of them, several orders of magnitude more of them. And also the distance constraint will also improve by the signal-to-noise ratio for a lot of them. So that is why. Yeah.
We have time for one last question. And okay.
Can we use galactic binaries for these type of analyses?
Can we use which type of binary, sorry?
Galactic binaries, so like double white dwarf binaries, which are not black holes or neutron stars, something like that.
So for cosmic expansion rate, you want to go outside of Milky Way. So galactic sources doesn't help here.
How about extragalactic DWDs?
For which type of sources?
So like DWDs which are outside our galaxy, would that be something that you're looking at?
If they are far enough, then yes, outside of the local cluster, local group, yes.
Okay.
Yeah.
Thank you.
All right, let's thank Hsin-Yu again. Thank you so much. And next up, we have Laura Blecha from the University of Florida.
All right, thank you very much. And thank you to the organizers for inviting me to speak to you today. I am going to talk about the current status and future prospects for modeling gravitational wave signatures of massive black hole binary populations. And I'm going to emphasize what we can use from what we're learning from PTA data, pulsar timing arrays, to prepare for the LISA era. So, first of all, supermassive black hole binaries are extremely powerful gravitational wave sources. We've heard a fair bit about that during this conference so far. And the frequency regime that is relevant depends on the mass regime of the supermassive black hole binaries that we're probing. So LISA will be sensitive to the millihertz frequency regime, which corresponds to the lower mass end of supermassive black holes, while pulsar timing arrays are sensitive to nanohertz frequency gravitational waves, which corresponds to the most massive supermassive black holes. So I want to highlight a few key differences between the LISA and pulsar timing array regimes. So as I said, LISA is sensitive to the millihertz regime, corresponding to lower mass black hole binaries, less than 10 to the 7 solar masses or so for the peak sensitivity. And LISA will also detect the actual merger events of supermassive black hole binaries. And it is able to detect these out to very high redshifts, as we heard in the last talk. Now, pulsar timing arrays, on the other hand, will detect the in-spiral phase of supermassive black hole binaries rather than the merger event itself. And they're foremost expected to detect a stochastic gravitational wave background due to the superposition of a cosmic population of supermassive black hole binaries emitting at different frequencies and redshifts. And PTAs are also going to be sensitive. The signal should be dominated by the loudest sources, which we expect to be predominantly low redshift sources below a redshift of 1.5 or so. So I won't belabor the point about how LISA works or how it will function to this room full of world experts, but we haven't heard as much about pulsar timing arrays, so I will take a minute to talk about how they work. So pulsar timing arrays observe suites of millisecond radio pulsars. So these objects that spin around at some millisecond frequencies and are able to emit these pulses of radio emission like a lighthouse sweeping around. Makes them extremely, extremely precise cosmic clocks. And so if we observe an ensemble of them for long enough, we can look for timing deviations that might correspond to the change in the path length due to the passage of gravitational waves between the pulsars and Earth. So this schematic on the right here, this animation, is visualizing that and how these timing deviations can be tracked. And so there are numerous experiments around the world that are attempting to measure gravitational waves using pulsar timing. The North American Nanohertz Observatory for Gravitational Waves, or NanoGrav, is one of them. That's a collaboration that I'm a part of. And so we can search for specifically timing deviations from these pulsars that are correlated between different pulsars, right? If we just see delays from one, we have no idea if it's systematics in the pulsar or space stuff, gas and dust between us and the pulsar. But if we look at enough of them, this is showing the relative positions of the pulsars that were observed for the NanoGrav 15-year data set. If we look at enough of them, then we can look for correlations between the angular separation between pulsars in the sky and the amount of signal we see. And specifically, we are looking for this black dashed line called the Hellings and Downs curve, first derived by Hellings and Downs, which tells us that these correlations we're seeing are produced by gravitational waves passing between the pulsars and Earth. And the blue error bars there are the measurements from the NanoGrav 15-year data set showing evidence for a gravitational wave background is characterized by this Hellings and Downs curve. And then simultaneously in 2023, other pulsar timing arrays around the world also published evidence of gravitational wave background signals. So in addition to simply detecting the presence of gravitational waves, we can look at the frequency spectrum of gravitational waves versus frequency. And that's what's shown here for the nanograv measurement in the top left, as well as for the EPTA, the European and Indian pulsar timing arrays, and the Parkes pulsar timing array in Australia. And so all of these show consistent results, and they are also all have these power laws fit to them. And part of the reason for that is that the simplest prediction that you can make for the gravitational wave background you should get from supermassive black hole binaries, a population of them throughout the cosmos, is this power law. Now, as I said, this is the simplest model you can make. Of course, things can get a lot more complicated than that, and that's where the fun begins for us theorists. So I want to talk about more of the details about how these black hole binaries actually form and create gravitational wave signals. So galaxy mergers create supermassive black hole binaries in the first place. We know that generally all galaxies have a supermassive black hole in their centers. And so when two galaxies merge together in the normal process of the hierarchical buildup of structure throughout the universe, then it brings together a pair of supermassive black holes, which can then in-spiral further in the merger remnant and eventually produce a supermassive black hole binary. But one of the things that makes this a very challenging system to model is the vast range of physical scales that the black holes must traverse between the initial infall of those galaxies, bringing them together, and their actual merger. So the galaxies, that animation I was just showing was maybe visualizing galaxies merging on roughly 100 kiloparsec scales. But the black holes have to then continue to in-spiral through dynamical friction in the merger remnant, and then their in-spiral must continue to be mediated by their astrophysical environment, perhaps via individual stellar scatterings, removing orbital energy from the binary, or gas drag from a circumbinary gas disk, or a combination thereof, before the black holes can finally get to the regime where gravitational waves are dominating the in-spiral and driving the black holes to efficient merger. And so the uncertainty in the efficiency with which this process happens is one of our major challenges. And so the other thing we can do, of course, is to try to look for electromagnetic signatures of this process in action. So there is a decent-sized sample at this point of dual AGN that have been measured. So that's dual active galactic nuclei, or pairs of accreting black holes in merging galaxies. But those are on more like kiloparsec scales, so still very, very far outside the regime where gravitational waves are relevant. And there is scant evidence for black holes on roughly parsec scales. This is one classic example, but there's really not a lot else that's been confirmed at those scales. And then there is a whole host of candidates on subparsec scales. We heard a lot about this from Maria Carisi in her talk, that we can identify time domain signatures of variability that may correspond to binary orbital motion. But again, these are candidates. Confirming them and distinguishing them from false positives is an arduous process given their years-long orbital periods. So hopefully, there's a lot of reason for optimism that the advent of a new era of time domain astronomy will really make progress on that front. But in the meantime, we really want to try to do a better job of understanding how these black holes are coming together and merging, and even when we do see these EM signatures, matching them to the larger population of dark supermassive black hole binaries that aren't actively accreting remains a challenge. And this challenge is not just a matter of nuance or an academic exercise. This is really an existential question for observing these systems with LISA, because there has, for decades now, been some level of debate about whether supermassive black hole binaries can even merge at all. It was first pointed out by Begelman, Blanford, and Reeds in 1980 that there simply may not be enough stuff in the centers of galaxies to drive the black holes together to the point where gravitational wave emission can take over and merge then within the age of the universe. And the crux of the problem is really that the scaling of the time scale for the black holes to merge through gravitational wave emission alone is a very steep function of the black hole separation, which means that very close black hole binaries merge very quickly, and wide black hole binaries can take many times the age of the universe to merge through gravitational wave emission alone. So the efficiency of this middle bit here is crucial importance for predicting the merger rate. This is often characterized as the final parsec problem. And there have been many, many, many solutions proposed to this final parsec problem in the 4.5 decades since it was first pointed out. But of course, the devil is in the details, and we really need to understand the actual likelihood in various environments that the binaries are going to merge as a function of redshift within a certain amount of time. Happily, we have some real progress on this front with pulsar timing arrays, and Helly, the Hellings and Downs curve, is ready to weigh in. So if indeed the signature seen by pulsar timing arrays is coming from a population of supermassive black hole binaries, as we think it is, then this is the first robust evidence that black holes overcome the final parsec problem and merge. Now, I said that pulsar timing arrays are not probing black hole merger events, but they are probing black hole binaries that are very deep into the gravitational wave dominated regime. So once they get to that point, they will merge efficiently, and thus this is highly informative for LISA. So that begs the question, what else can we learn about black hole binaries from pulsar timing arrays? So this is where we can get into the details of how we model these populations and try to infer something about them from these gravitational wave observations. And there are a number of different ways, complementary ways to go about this. So one is to use a cosmological hydrodynamics simulation as the basis for the galaxy and black hole populations. And then with these cosmological hydrodynamic simulations, we're directly solving the equations of gravity and hydrodynamics from very early universe to today, but we cannot resolve a lot of the small-scale processes like black hole accretion, star formation, and black hole binary inspiral. So we have to use subgrid models and or post-processing models. So this is an example of a post-processing framework for black hole binary inspiral built on top of the illustrious cosmological simulation. We can also use semi-analytic models where the basis for the galaxy and black hole population is either an analytic merger tree or, more commonly nowadays, a dark matter only cosmological simulation onto which all of this entire framework of galaxies and how they form and evolve and how they co-evolve with their black holes can be built. And so this is one example of that, the L Galaxies semi-analytic model. And then still another approach is to use our empirical constraints for the aspects of these models that we do have EM observations of, and that includes the galaxy stellar mass function, so the distribution of galaxy masses, includes the empirically observed galaxy merger rate, and it includes the relationships between the black hole masses and the host properties of the galaxies they live in. So if we take all of those things and our best estimates from EM observations of what those should look like, and then combine them with a simple model for binary evolution, then we can make predictions for gravitational wave background spectra and then compare them with observations. So this is what we did in the nanograv analysis for the 15-year data set. And just to give you an idea of how the binary evolution models part of this plays into it, so the top panel is showing in-spiral timescale versus binary separation. The innermost timescales, which are on the right hand of this plot, are set by GR, so that part is well known. and then it's, as I said, this middle bit that is least certain. And so if we change, so this is just modeled all as a broken power law in this instance. And so if we change this power law index for this efficiency of the in-spiral here, then it changes the shape of the gravitational wave background spectrum. And so in particular, if the green curve, if you focus on that, that transitions to the gravitational wave dominated regime earlier at a larger separation, which means that the black hole binaries emit more gravitational waves as they're moving through those portions of the separation space towards merger. And so we get something that looks closer to that analytic power law approximation that I showed earlier. Whereas if they transition from the astrophysically dominated to the gravitational wave dominated regime later, as shown in the blue curve, then the black holes are moving faster through those frequency bands than they would via gravitational wave emission alone, and that's what causes this attenuation or turnover at low frequencies. So this is this plot is showing the best fit models for our analysis of the 15-year gravitational wave data set. And there are a few interesting highlights here. The first and main one is that we find that pulsar timing array results are indeed consistent with a population of supermassive black hole binaries. I'll note that similar analysis of the EPTA results has also found consistent findings with this. And we're seeing possible hints that there is indeed some spectral attenuation or turnover happening in the gravitational wave background. So the blue and orange curves here, the thick lines are the medians of these realizations, are when we include some sort of astrophysical driven in-spiral into our models, versus the purple, which is a gravitational wave only model. And so the former are arguably a better fit to the data here. And we also find hints that black hole binaries are more numerous and or more massive than we expected. And that basically just means that when we put in all of our empirical models for the galaxy and black hole populations with the best fit values from EM observations, the gravitational wave background amplitude is higher than what our zeroth order model predicted. We can reproduce the observations, but we have to tune some of those parameters upwards. So to give you an idea of how that works, these are the 6 parameters that were varied in the inference that was done for our analysis of the 15-year data set. The 2 panels on the left here with the green curves are showing variation, systematic variation in the galaxy stellar mass function. So the normalization and the characteristic mass of the distribution of galaxy masses. And then the middle 2 panels show the normalization and scatter of the black hole mass galaxy bulge mass scaling relation. So more massive galaxies means more massive black holes for a fixed scaling relation. And then more massive black holes at fixed galaxy mass also is going to raise the gravitational wave background amplitude. In the right 2 panels, we vary the 2 key parameters that control the binary in-spiral model that we have there. So you can see already at a glance that there is some degeneracy in the variation of these parameters and how they affect the gravitational wave background. And indeed, the posteriors we get from this analysis are very broad. So we're in the very early stages of being able to say anything about supermassive black hole binaries and their population characteristics from gravitational wave data. But we're doing it, which is super exciting. So in the future and in our ongoing work, we are continuing to take data, which will improve our constraints with future data releases. And then also, we're working on improved methods for modeling and for performing this inference of the gravitational wave data. And so I'll just highlight one of those efforts here. This is some work that I'm wrapping up now that basically is a different parameterization of the binary in-spiral that is designed to optimize its sensitivity to pulsar timing array data. But the thing I want to highlight here, so watch for more details on that in the coming weeks, but the thing I want to highlight here is the well-known result, which is that as the gravitational wave background amplitude varies by 2 or 3 orders of magnitude, with significant variation in the shape as well, the binary in-spiral timescale, shown on the right here, varies by more like 9 or 10 orders of magnitude. All right, so this whole issue of how efficiently black hole binaries in-spiral and merge is crucially important for LISA, even more so than it is for pulsar timing arrays. So that is all the more reason to put as much effort as we can into using these PTA data to constrain our models that we can use then to make LISA predictions. I'll just highlight one more recent effort to use the PTA data to constrain black hole populations, which is this work that was done by Kayan Matt, a PhD student in nanograv who's at University of Michigan, working with Kai-Hon Gultekin. And Kayan looked at the redshift evolution of the black hole galaxy bulge scaling relation and how that affects the gravitational wave background. And they showed that the best fit model for nanograv, the 15-year data set, includes positive redshift evolution for both the scaling relation amplitude and scatter, which means more massive black holes in a galaxy of given size as you go further back in time into higher redshift. And so this alleviates some of that tension between our best fit models with no redshift evolution and the gravitational wave background amplitude we're seeing. And this is also very interesting because JWST is also seeing evidence for redshift evolution of the black hole scaling relations. So JWST has found more accreting black holes, more AGN at high redshift, and more massive AGN than anyone predicted. And by some estimates, they are wildly overmassive compared to their host galaxies relative to local scaling relations. And so this is really transforming our view of the high redshift universe and making it even more exciting to think about what LISA will reveal. We certainly have this population of massive black holes in the very early universe. And so this gets to another fundamental open question in our field, which is how these supermassive black holes that I've been talking about for 23 minutes formed in the first place. We don't know. We have some theories. There are little cartoon bubbles here to illustrate where those theories might land in this redshift mass space here. I could give a whole other talk about the details of those theories. We have a lot more details than cartoon bubbles. But the real point is that we don't know, and LISA is our best chance to find out. And so that's sort of visualized in this plot from the LISA astrophysics white paper, showing that the LISA detections will really probe lower masses and higher redshifts than we can with other means. And I've gone ahead and added a little JWST bubble here and PTA bubble here to show how all of these different experiments fit together and complement one another to build a picture of supermassive black hole evolution across cosmic time. So just quickly before I conclude, I want to emphasize that one of the reasons that LISA is such a promising probe of black hole formation is because just as the in-spiral timescales are uncertain and very important for LISA event rates, so are the formation channels. So they have a big impact on the LISA event rate and its evolution with redshift. And that's shown here, both for a semi-analytic model result with different seeding models from Ricarte and Natarajan, and then also from these cosmological simulation results from the Brahma simulation suite developed by my former postdoc, Aklan Bomek. So there's a lot of variation depending on what you assume about black hole formation channels in the LISA event rate. And just to highlight that even our most lenient seeding models are having trouble producing the most extreme high redshift JWST AGN. So that points to maybe even more lenient seed models, maybe also more efficient accretion at these very early times. And it's also possible that some of these masses are currently overestimated and might come down. So again, lots to explore in the run-up to LISA. I just want to finally highlight a few projects that are being led by students, student projects that I've been involved in that are related to black hole binary evolution. All of these students are here at this conference, so please find them, ask them about their cool work, and I will leave my summary slide here and take any questions. Thank you.
All right, we have our first question over there.
So Laura, how would some of those conclusions you had on the population change if hypothetically the nanograv amplitude was to drop by a factor of 5 and the spectral index was to steepen by, say, a power of frequency? So
if the amplitude isn't as low and it's
steeper.
And it's closer to a power law.
Yes.
So I think that would favor, again, there's degeneracy in the parameters, right? So that could mean that we don't need to push the galaxy stellar mass function or black hole bulge scaling relations up. We don't need as much redshift evolution, or we don't need as much efficient in-spiral to create the amplitude. But if the spectrum is closer to power law, then it has to be pretty optimized in terms of where that black hole enters the gravitational wave regime. Yeah.
We have another question right up here.
So I've also heard the argument that the host galaxies for the big black holes are so different than the host galaxies for the LISA black holes that you don't get much leverage from PTA rates. So what is the current state of that argument?
So I think that, we are not going to get perfect predictions of LISA event rates from PTA data. That's just not going to happen because they are at very different mass and redshift regimes. But no one has, until we had these PTA data, we literally had only electromagnetic constraints on the LISA black hole population. And now we have both electromagnetic and gravitational wave constraints. And so, yes, there's still going to be a lot of wiggle room, in part because of, like I said, you vary the PTA amplitude by 2-3 orders of magnitude. You can vary the in-spiral timescale by 10 orders of magnitude, right? So there's just inherently a lot more variation. But I do think we're going to start improving things, especially because we're seeing evidence that redshift evolution may be part of this, right? We're not just an anchor at redshift 0 with PTA data, right? Those binaries have to form at higher redshift, first of all, and evolve to merger. So we're learning something about, maybe the redshift 2-3 black hole population. And then also if we can start constraining something about the redshift evolution of the black hole population, then I think that's also going to help our highest redshift models as well.
All right, we have time for one last question. If not, I can maybe take advantage. Would you mind flipping back to the slide from the white paper, there we go. So I'm really keen to understand this. My question is similar to Tyson's, but I'm trying to understand what it will mean if we, in the LISA data, are able to identify, let's say, two salient populations. Let's say, we often think of heavy seeds or light seeds, but let's say something that is more massive, high redshift, lower mass, lower redshift, or vice versa. What do you think how will that help us connect to what you're observing in PTAs?
Yeah, that's a great question. So I think that, first of all, this is where we also need more theoretical work to say, okay, we see this in the LISA data, what is that really telling us about seeing? And what are the various scenarios also in terms of degeneracy of formation versus early growth? So there's still plenty of theoretical work to be done in that space. But I also think that we're seeing some very interesting hints from JWST that heavy seed models are maybe going to have an easier time producing the population of black holes that we're starting to observe. And so I think that if we see something that supports that idea in the LISA data, then that's going to really help us build a more complete picture. If we don't see any heavy mergers and they're all like POP3 stellar remnants at redshift 20 or whatever, then that becomes a really interesting challenge for how did they grow, from then to the JWST population. So yeah, that's sort of, I think, how we can start to tease out the different pathways.
Fantastic, thanks so much. Let's thank Laura again. And our final speaker for today's final plenary is Tyson Littenberg from Marshall, and just setting up here.
Okay, hi everyone. Ann told me I have to go fast, so buckle up. We're going to talk about the LISA Global Fit, and then you're going to go to lunch. So what I'm going to try to communicate to you is that we actually do need a global fit. You've heard this a million times. I hope when you walk out of here, you believe it. This graphic, I love this graphic. It has shown up in many talks this week. It will show up in many more talks this week and on into the future. And it is often used, I often use it as a hand-wavy way of saying we need a global fit, because you say, oh no, look at all those sources. What are we ever going to do? Let's fit them all together. I think we can do a little bit better now because the DDPC is really strengthening up its simulation capabilities. Still use that cool graphic, it's lovely, but let's take a closer look at building up some LISA data. So what I've done here is I've zoomed in on just a few hours of LISA data. Remember, LISA data will last for many, many years. This is a tiny little slice of the LISA data. And there you see a black hole on its way to merge in a few days. If you're paying close attention, you can see that the peaks are at different heights as you go. That's because we're close enough to merger that you're starting to see those higher harmonics. And then on the right-hand side, we can see the power spectrum of that black hole for the full data set. So now what I'm going to do is I'm going to stick on top of there an emery source. There's the emery source. Okay, so now you see a bunch of little spikes as the emery is passing close to the central black hole. And that doesn't look so bad. That you can tell that they're at different frequencies. You can tell that the timescales are a little bit different for them. We'll also throw on one of these stellar origin black holes. Okay, now it's getting a little bit crowded, but you can tell in the power spectra that the stellar origin black hole is just like a little spike. So that's pretty easy to pick out. These things are all fairly separable. So I've add all these three sources together. It looks a little bit messy, but manageable. It's not too bad. Okay. But you have to remember that these things don't live in isolation. There is a population of these stellar origin black holes that we have to contend with. Only a few in this data set. Many of them actually got band-passed away from the image that I'm making, so there are a few more at higher frequency. But it's starting to get a little crowded here. There's also a population of emeries, and as we've heard this week, we might be grossly underestimating what that population of emeries could be. So it's getting a little rough, and now we're having to change the vertical scale on this plot to get everything in. Okay, so we'll put all that together. And now you might not be feeling so great about easily being able to pick apart these sources. But there's also a population of these supermassive black holes. And while they're transient, they just completely dominate the power spectrum. So they're very, very loud sources. They're just going to completely swamp everything else down below. Okay. We've never actually observed any of these sources before, but we have observed our white dwarf binaries in our galaxy. We know of several dozen of them already, so let's throw them on top. Okay? And those are just the tip of the iceberg of what we think is a population of tens of millions of these white dwarf binaries that we have not yet observed, which is why we need to build LISA. And now we just completely blow this thing out when we put the galaxy on top. Okay, so if I combine all those together, this is starting to look an awful lot just like noise, which reminds me that I forgot to include instrument noise. So we'll put some instrument noise on top, okay? And it's kind of remarkable that the instrument noise is like almost an also ran in this particular slice of data using this particular bandpass. There are places where the data will be completely dominated by signal, not noise. So on ground-based astronomy, gravitational wave astronomy, you're digging through noise to look for signal. There will be parts of the LISA data where we're digging through signal to try to find the noise so that we can tell our instrumentalist friends that the machine is working. Okay, so let's put all that together. Let's zoom out, and here we have our mock data challenge that we're gearing up to analyze this summer, where you can see the full 2 years of data with all those different sources on top of each other. You see the big spikes from the black hole mergers. You see the galaxy modulating. It's a hot mess. Okay, that is not what we get. What we get is the combination of all those things, and it's our job to build pipelines that can work all the way back to seeing all those individual sources in the first place. This is hard. So there's 2 ways to do it. So one way to do it is to just say, I'm just going to go through and pick off the brightest source and work my way down, and people seriously considered this 20 years ago and tried it. And what they learned is that you have to repeat this process so many times that it gets quite complicated as you go through several iterations. Another idea is to just say, to heck with it, I'm just going to build a gigantic model of the entire data set. I'm going to try and fit everything all at once. That's the global fit idea. Okay, so the downside of the hierarchical model is that you have to do so many of these iterations because there are so many sources, something like 10 to the 5 detectable sources, or sorry, 10 to the 4. The downside of the global fit is that if you parameterize all those sources, it's something like 10 to the 5 parameters. So you have to optimize a 10 to the 5 parameter model, which is no small task. So this debate raged for many years. And let's say, forget about it, we're just going to do the hierarchical analysis anyway, okay? What sort of problems will you encounter? You're going to encounter that there's no such thing as a perfect subtraction. So you take that brightest source, you do your best fit to it, you subtract it, there will be a residual. There's no such thing as a perfect subtraction. The more and more iterations you do, the more and more those residuals will start to build up, and it eventually limits your sensitivity. The instrument noise doesn't limit your sensitivity, your ability to cleanly subtract signals does. That's a bummer. You will also screw up sources that are correlated with each other. So if they're overlapping in time or frequency or both, if you pick parameters of one source, that would affect parameters of the other. And if you ignore those correlations, it will introduce biases in your parameter estimation. That's also a bummer. And then finally, the uncertainty you have in one subtraction should contribute to the uncertainty you have in the other. And if you're just doing this hierarchically, you're basically taking many, many slices through this really big parameter space, and you'll underestimate your statistical error, also a bummer. The downside of the global fit is just really big computational challenge, but we have really big high performance computing now, so let's do that one. Okay, so I've explained this in pictures, I've explained this in words, and now I will bore you and explain it very quickly in math, and then all types of learning will be covered, and we will all be on the same page that a global fit is necessary. So the central engine of our data analysis is Bayes' theorem, which is shown up here, and the workhorse of Bayes' theorem is the likelihood function, which tells how well our model for the data is predicting the observed data. So if we look at that likelihood function, it contains this inner product, which is data minus model. And then there's also some model built into the covariance matrix, which you can't see in this inner product, but that's all in there too. Okay, so let's now think about the likelihood function in this global fit context. We don't just have one source that we're subtracting to do the inner product. We have many sources that we're doing. We don't have one set of parameters to describe a signal. We have a set of many parameters to describe all the sources in our data. So we have this bunch of different parameters we have to fit all at once, and we have this sum of all these waveforms that show up in our inner product, plus the covariance matrix bit. Okay, so now we're going to take that inner product and just chain rule it up and separate it into all of its little parts. Okay, so we have data inner product data terms, who cares, those are constant. We have data inner product individual waveform, no problem. We have individual waveform inner product with itself, no big deal, that's just the signal to noise ratio. And then we have this last term, which is inner product of waveform M with waveform N. So those first set we can just ignore, those don't really matter. And what is important for the context of the global fit is the inner products of waveforms with other waveforms in the fit, okay? Remember we said there are something like 10 to the 4 detectable signals. So if you think of how many combinations there are that you have to think about for these waveform inner products, it's something like 10 to the 8. So even if you say, it's very rare that 2 signals will actually have some non-zero inner product, we have 10 to the 8 rolls of the dice to find one, and that will happen.
Okay, we did pictures, we did words, we did math, you're convinced, so now let's just build one. So how do you design one of these global fit pipelines? So one of the issues is that the parameter space is so large, it's going to be impossible to do a grid-based search like has been used in the ground-based detectors. So we've uniformly moved to these stochastic sampling algorithms. Markov chain Monte Carlo is one example, but there are many others out there nowadays. The other issue is that we don't know how many sources there are. There could be 10,000 galactic binaries, there could be 9,999 of them, there could be 10,015 of them, and then all the other source types as well. And so we can't just pick different models and compare them at the end, we have to do all of this simultaneously. And so our stochastic sampling methods have to also be transdimensional, and a classic example of this is the reversible jump Markov chain Monte Carlo. If you've never heard of the reversible jump Markov chain Monte Carlo, it's rad. The number of parameters in your model is one of the parameters of your model, which gets people pretty excited. So let's just very, very quickly describe what a transdimensional sampling algorithm is. So think about something like MCMC or nested sampling or whatever. What you're doing is you're stochastically exploring parameter space with a model. And the idea is if you do it properly, the amount of time your model spends in a volume of parameter space is proportional to the probability that that portion of parameter space represents the universe in which we live. The trick with the transdimensional sampling is that you also allow it to explore different models using the same rigorous statistics. So now you're doing your model selection and your parameter estimation all at the same time, and you can say the amount of time I spent in a particular model, and then the amount of time I spent in a volume of that particular model tells me the probability that this is the right model and those are the right parameters. Okay, that's all we're going to do talking about MCMC and its friends. But let's say you think this is insane, it's still too many parameters, I don't care about how big your computers are, this is never going to work. We have a plan. The plan is to deal with this very large dimension space is to use something called a block Gibbs sampling scheme. Okay, more jargon. So a Gibbs sampler, don't worry about the blocks now, is let's say you have a 2-parameter model and those parameters are highly correlated. What you can do is you can hold one parameter fixed. I think in this example we hold A fixed and then just sample over B, and then stop and hold B fixed and sample over A, and then repeat, and then keep repeating, and then eventually you sample over the whole space. For you can just tell from this drawing, for highly correlated parameters, this is a very, very slow way to converge, and so it's better to be smart and jump along the correlated directions when you're doing your stochastic sampling. Aha, but when we think about the LISA global fit problem, I told you these correlations are important, but I also told you these correlations are rare. They might be small, we can't ignore them, but they don't have to ruin our lives. So what we can do is we can block together our parameters for sources that we don't think have strong correlations, and we can hold one block fixed. Let's say we hold our UCB model fixed and adjust all of our massive black hole parameters for a while, and then hold our massive black holes fixed and adjust all of our UCBs, and rinse and repeat. So this is pretty handy when your source types are uncorrelated. It allows you to develop these blocks independently, so we could have team MBH and we could have team UCB, and as long as we agree on the interfaces, we can merge these things together when it's time to actually do the global analysis. This is also sort of parallelizable. You got to be a little bit careful here, but if you know for a fact that block A has 0 correlation with block B, like really, really 0, you calculate those inner products, they are 0, then you can update those blocks independently at the same time and parallelize part of this effort. And then last but not least, because it's all modular, that's swappable. So you can develop one block and then someone else can have a better idea for how you do your emeries. And as long as you agree on the interfaces, then you can just swap those in very easily. You don't break the whole global fit by fixing one block. Okay, so then the big scary global fit likelihood with all those correlations in it gets reduced down to a block only has to care about the residual from what all of the other blocks have taken away, update its fit, and then pass its information to all of the other blocks, and they just keep sharing this information, and I'm gesturing in a sort of circular motion because this is sort of the picture that we have in our head. So here's a cartoon of how the whole global fit works. This was inspired at one of the early LISA Consortium meetings in Marseille, where we were sitting there looking out at the Ferris wheel and coming up with this architectural design for the global fit pipeline. So I stole this diagram and then prettied it up from Neil. So the idea is that data goes in, you develop all of these blocks individually, you keep iterating around as they're just passing their information via the residual to all the other blocks, and then samples come out the other end, and you've done your global fit. Okay, so you might not believe me that this is possible. I'm going to prove to you that it is. So we've done a few demonstrations of this on a smaller scale data set. The last of the LISA data challenges, LISA data challenge number 2, was the first demonstration of a global fit having multiple source types together. Many groups developed software, many groups successfully did this global fit, and we've been comparing outputs ever since. So this data challenge included massive black holes, the white dwarf binary population, and we put in by hand the known white dwarf binaries. And then a bunch of groups went away, and we're able to actually separate out. So this is a look at all of the reconstructed signals from this simulated data. So the purple are the white dwarf binaries that we were able to recover. The orange are the known binaries. The pink swoopy thingies are the massive black holes. And this is starting to look like that picture that I started the talk with when we put all those signals together and then said we had to work backwards. So we've done it once on a smaller scale data set. It was just a year. There weren't as many parameters. But you know, we've got some time to expand the capabilities. Okay, and there's a zoom in so you can see all these white dwarf binaries sitting on top of each other and the black holes swooping through. It kind of looks like that picture that we started with, but this is in the frequency domain. Okay, so we're going to build global fits. Who is going to build global fits? Lots of people are going to build global fits. As far as the LISA project is concerned, there are 2 parallel efforts for global fit development. So there is a global fit development happening on the NASA science ground segment side, and there's a parallel effort at the DDPC of developing global fits, multiple pipelines in development right now. So then you're going to say, well, what do I do when I have real data? Don't worry, because these different global fits are all going to receive the same spacecraft data. They're going to do their work, and then at the end, the results will get combined into the source catalogs, and so you, the consumer of LISA data, can pick your source catalog. It will have the combined information from all these global fits, and then if you really want to get into the weeds, you can work your way backwards through all of the intermediate processing steps if you want to go to a lower level of data. Some of these global fit activities are open source development, so I believe this is being recorded or something, so you can actually get the details here, but there are 2 GitHub collaborations that are open source that you can come and see our work in progress. And then once we are moving on into making production pipelines, there will be like steady controlled data code releases that will go along with the data releases. Okay, when will you have a global fit to play with? Really, really soon. So you've heard during this meeting that the big activity right now is working on this Common Dataset 1, the light version, which is the first time that we will include EMRIs and stellar origin black holes in one of these global fit exercises. We've also made the massive black hole models a little bit more realistic, and the data set is now 2 years instead of 1, with slightly more realistic orbits, which makes the LISA response function more difficult to calculate, but we know how to do it. So here's a time frequency picture of this Common Dataset 1, so you can see the black hole mergers, you can see the galaxy sort of coming into and out of view as the constellation moves around, and if you really stare at it long enough on a late night, you might convince yourself you can see an EMRI. Okay, so here's that cartoon picture now, where we're covering most of the blocks that we had thought about. What we've left out are like transient noise or signal sources like gravitational wave bursts, other data issues like gaps, or non-stationary noise, and we've left out a stochastic background for now, but all this stuff will get added into the next common data set. And now, with the time that I have remaining, I'm going to give you a very quick tour of the very bleeding edge of development, both on the NSGS and the DDPC side, so you can see where we are putting this all together, and then sometime in the fall, winter, we should actually have some consolidated results. You've heard that the zeitgeist is to move away from doing analysis in the frequency domain towards the time frequency representations of the data. So this is what a PSD looks like now for LISA. It's not that swoopy thing with the little squiggles at the end. It just looks like this big, beautiful, colorful blob. And if you zoom in to those dark bands at the top, that's where the noise and the detector response go to 0. That's due to the geometry of the constellation. And if you zoom in on that in this common data set, you notice that those wiggle around. The reason they wiggle around is because we have these more realistic orbits that don't maintain an equal arm constellation the whole time. And so my big takeaway for this part is that even when you have stationary LISA noise, it ends up being non-stationary because of the motion of the constellation itself. So just give it up. Stationary noise is over. It doesn't matter how well the engineering teams do building this thing. LISA noise is non-stationary. We're moving on. Okay, so we have a model for this time frequency noise that's modeling the noise at the link level. So we have how the test mass is jiggling around in each link and how the metrology noise is fluctuating in each link. So at low frequency, it's dominated by test mass. At high frequency, it's dominated by metrology. And then we also can stick on the galactic foreground, which is also non-stationary due to the motion of LISA. So we have this non-stationary noise model now that can follow those oscillations as they go. And the corner plots on the right here are to convince you that I'm not lying. The team on the DDPC has provided us with some validation results showing that they're able to do parameter estimation runs on the massive black hole simulated data and show that they're getting robust parameter recovery from those. And so it looks like all of our massive black hole waveform conventions are lining up, and we're able to do a good job of recovering those signals. So the massive black hole module is looking to be in pretty good health. We've done the same thing for the EMRIs. Many EMRIs, doing the EMRIs in the WDM basis and these time frequency bases is pretty exciting stuff. They look really cool in these time frequency maps. Groups have started looking at the recovery of the galaxy, so this is taking the first 9 months of that data. Right now we're just starting the samplers off at the input value for the galaxy and then letting the reversible jump do its thing to get down to a nice looking residual, and then soon the search will come in behind it. And then with just a few minutes left, I want to just tantalize you with things that are coming for the next data challenge. The heavy data challenge is going to include things like glitches, gaps in the data, and stochastic backgrounds. And so we've already started working on our stochastic background development. This example is able to provide you with an upper limit, even if there is no stochastic background. And you see, it doesn't look like a lot, but it's not a log scale, but the upper limit actually improves if you account for the non-stationarity in the noise. Also, you can actually inject a bright stochastic background signal like on the right and properly recover its parameters. And then we have work starting on a glitch model, adapting some stuff that was used for LIGO glitch mitigation to the LISA context. So this is a glitch put on the test mass, so it shows up in just two TDI channels and not the third. That's the top row. And then the bottom row, you can see that glitch was cleanly removed from the data. We still have some work to do filling the gaps. There was a great talk yesterday about gap filling, and we need to incorporate that into our analysis as well. And so, give us another couple of months, next LISA Symposium or sooner than that, we'll be able to take these full global fit data sets and work our way backwards towards the input signals and then give you the results, and you can go do all the science. Thanks, everybody.
Thanks, Tyson, for being dramatically on time. Like, I wish everything was like this, but this gives us way more time for questions. I see loads in the audience. Let's start from over there, but maybe we can get a mic on this side and a mic on that side so that we're more efficient.
Hi, Tyson. Great talk. I was curious, what is the reason for not for bringing stochastic gravitational wave backgrounds into these test data sets later? Like, why not earlier? We know they're there.
Maturity of both the simulation capabilities and the analysis capabilities, and then also just trying to figure out what kinds of stochastic signals you want to input. That we know, we really hope they're there. They're super cool. They're not going to really screw up any of the other analyses. A stochastic signal is not going to bias your ability to find a redshift 1 black hole merger. So they were just lower on the pecking order of things that we had to demonstrate.
All right, I'm going to take a question from over here, but you guys keep running around. Free mics.
Yeah, nice talk. I was just wondering, what if somebody wants to add a signal that's not in the original catalog that was used for the global fit? Will it be possible for people to pick up the current catalog and like continue the global fit, adding in new signals?
Yes, so the first level of entry to the data is the consolidated catalogs, but all of the input to that, including just the raw global fit samples or the raw level 1 data that was used upon which the global fit was run, are also part of the data releases, as is the code that is used to produce those. So if you want to go all the way back to level 0.5 and build your own TDI channels and run your own global fit by taking the existing pipelines and then just swapping out a module or sticking in something there, that is available and strongly encouraged.
You just need a big enough computer to do that.
You need a big enough computer, but you can do a lot of work just on the residuals, which you can create from the level 2 data to sort of pilot everything. And then when you're ready for your Nobel Prize winning paper, then you turn on the big computer for the global fit.
Actually, I had a question related to that. Sorry, Tyson, over here.
Here you are.
We have a lot of mics. It's kind of fun. We can duel. So the computational time, how much computational time did it take to do that second LISA data challenge, and how do you think it's going to scale as you move towards reality?
Yeah, so I can answer, we had multiple pipelines. I can answer to the one that I was shepherding. It took about a week on a few hundred CPUs. We've moved most of the development towards GPUs. And so for this CD1L exercise, we're planning on order week on order 10-ish GPUs, but we're still mapping that all out. As the number of, the MREs are really the driver here, so as the number of MREs increases, so too do the number of GPUs. So if we do end up with these 10,000 resolvable MREs, it's going to be a little expensive, but the actual run times seem to be fairly manageable, and we know there's a lot more meat left on the bone to improve our efficiency and how the sampling is done, so I think we can get those run times down further without depending on like major hardware changes for the computing.
Yeah, Tyson, if in the blocked Gibbs sampling, if I really understand these different source classes as independent, how is that different than just fitting each source class kind of on its own like a hierarchical fit?
The difference is that what the block is fitting is the residual from what all of the other blocks have done. And so you change this other block, you update the residual, and then you keep updating the parameters in this block, and so you're naturally marginalizing over the uncertainty in all the other blocks. Whereas if you did a hierarchical fit where you're like, here's my massive black hole fit, I'm done, everyone else work with it, then you're just dealing with a slice of the massive black hole uncertainty instead of marginalizing over it.
Can you do like an independent check by leaving out source classes and seeing how the other parameters of the different sources remain the same or not?
Yeah.
That's your answer.
Hey Tyson, great talk. Another question on the Gibbs wheel. You had a specific ordering for your source classes. Is there a specific reason for that ordering, and how do you come to like that specific ordering?
If the order matters, you're doing it wrong. So it had better not. Right. That was the order that we wrote them down one time.
Great.
Hi, so if I have a very specific thing, like say I like IMRIs and I have IMRIs that are right at the edge of the, oh, did someone say something? I have IMRIs that are like right at the edge of the sensitivity curve. Like, am I gonna be waiting extra long to get like a global fit that I should trust for like picking out my sources, or like, is it gonna come just around the same time as everything else?
Oh, do you mean when we're operational? Or do you mean in this development phase?
Both.
Okay, so in the development phase, one of the hardest things right now, the thing that I would say is the least mature in all of this is the MRE search. So right now the MRE detection threshold is pretty much like I can see the MRE, and we're gonna try to work that down closer and closer to like the numerical limit. So if you have like just above threshold MREs that you would like a NSGS or a DDPC pipeline to find for you today, you're gonna have to wait a while. We'll make that wait time as short as possible. But during operations, everything should be up and running. But what you should look forward to is as LISA continues to integrate, the noise level actually goes down because you can remove more and more of the white dwarf binaries. So just because you didn't find your favorite MRE in release number 1 doesn't mean it won't be there waiting for you in data release number 2 and beyond.
Okay, thank you.
And thanks for the great talk. I was just wondering, what source populations currently pose the greatest challenge for the global fit?
Oh, that depends on the day. The MREs and the galactic binaries are the two drivers of the computational cost. So if your risk is fiscal, then I would say lots and lots of MREs or a very, very large galactic foreground are the things that are going to stress the pipelines to converge the most. The nice thing is that it's mechanical. Once we have this algorithm designed, it will work. It's just a matter of how much money can we throw onto the problem to get the solution.
Thank you.
Yep.
All right, let's take maybe one or two last questions. We have one here, one here. Oh, online. Maybe let's take one online because we've not looked online at all. Thanks.
Henry Wegner asked, do you need to model the noise floor / sensitivity as well?
Yes, and we do, right? So the first of the highlights of the current bleeding edge were our model for the instrument noise, and then we put the galactic confusion noise on top of that. We know that the instrument noise model right now is a little bit simplistic, but all of the machinery there is there that we can adiabatically improve that noise model as we get more and more input from the instrument team of what we should expect. But the hard part of just figuring out how to code up how you model the instrument noise is mostly a figured out thing. So then it's just a matter of what sort of non-stationary can we expect? Are there other sort of noise terms that we're missing there? But we feel like that's pretty under control.
Hello, Tyson. Hello, Tyson. Oh, is this on? Yeah. Okay, sorry. So the T channel is supposed to be noiseless, or only supposed to be comprising of noise and no sources in the low frequencies. Is that supposed to be used as a verification for instrumental noise later on, or is that going to be used at all in low frequencies?
So for the global fit analyses, we have abandoned using the A, E, and T combinations in favor of the X, Y, and Z combinations. And the reason we have done that is because we expect that there will be disruptions in the data, gaps, but we don't necessarily think the gap will take down the whole constellation. It might just take down one link. So if you take down one link for a little bit, your Michelson-like channel that doesn't involve that link just powers right through, whereas you need all 6 links to form the A, E, and T channels. So we think the pipeline is much more robust to using X, Y, and Z, and then just every once in a while, 2 of those will drop out because there's a gap in a link, and then they come back on and the code can just keep chugging.
Okay, thank you.
Yep.
All right, I think that's all, folks. Let's thank Tyson and everyone in the session again.
All right, thank you, Arianna.